All right. Hello, my friends. Um, I'm recording this from my home because, as I said in a previous announcement to the class, to all my classes, I have unfortunately contracted some nasty bug this week over the weekend. And I, while I am slowly on the mend, I do not wish to pass this on to any of you. So for my online students, this doesn't feel terribly different. For my in-person students, I'm sorry this had to happen on finals week, but we don't really control that, do we? We get sick when we get sick, so we'll just have to go with it. Today is going to be your final lecture as well as your final exam review. I'm going to go through this last PowerPoint. It's one of the shorter ones, which normally leaves plenty of time for exam review, but because of the odd circumstances surrounding today's session, we'll see how many of y'all sent emails. I won't be able to have any live in-person question Q&A session, obviously, so it's all dependent on whoever sent me emails, like I mentioned in my announcement. But let's get through this lecture first. Excuse me. If at any point I go silent for a minute, it's probably because I'm muting myself, so I could blow my nose or have a coughing fit or something. But I'm sure you all get it. You've all been sick before. All right. All right. Lecture 13: Crustal Deformation and Mountain Building. So we're going to talk about first mountains. Mountains are built as the crust interacts with other pieces of crust. What do I mean by that? Remember tectonic plate theory, okay? Namely that our crust is broken up into plates, like the different pieces of a broken eggshell. Remember, I used that as an example, where all of the eggshell pieces are constantly moving around the outside of your hard-boiled egg and are bumping into each other, sliding under each other, past each other, all of that, all of those different interactions. Well, each one of those interactions comes with a different kind of energy, a different kind of energy interaction, a different kind of force, okay, or stress. There are several different kinds of stress, okay. Now, the ways that materials respond to stress is an entire branch of science. I'm not even exaggerating that, okay. Materials physics is actually a very large and ever expanding field of science. So, how materials respond to stress is dependent upon A, what they're made out of, obviously, also how big they are, and what other factors are in play, right? What is the temperature? What kind of other forces are at play, like temperature? Maybe gravity is a factor here as well. Okay. Whatever happens, whatever forces are at play, you get deformation as a result of the buildup of these stresses. Okay, deformation is any change that occurs in a rock body. Now, this includes the size, shape, and orientation of your material, not the content. However, why not the content? None of these stresses are introducing new materials to the recipe, so to speak. Remember a chocolate chip cookie. I'm not adding walnuts to the original recipe here. I'm either changing temperature, I'm squeezing the dough, I'm stretching the dough. I'm not adding anything to the ingredients, right? So deformation does not include any of that. So the content of our material doesn't change, although we may get different minerals. Because remember, in these conditions, you might end up with metamorphic conditions because of the application of the stress and heat. And so you will get all of your original materials all those original materials will remain, but you could end up with a totally different mineral as a consequence of those materials reshaping themselves. Okay. But again, that's a change in the size, shape, orientation, not in the content itself. Now, what are the three kinds of stresses that we see here? Well, first we've got our compressional stress. That's the image you see on the top here. This happens in your convergent encounters between tectonic plates. Also, by the way, when we have reverse faults, okay, this is when you get that compressional stress. The forces, the unequal direction of stress is going towards each other, and so the layers of rock get folded. You remember that term? You get folding. We also get reverse faulting, um, and this is a squeezing sort of stress. Okay, you're compressing. That's why it's called compressional stress. The second one is tensional stress. That's a stretching force. This can happen when two bodies, when two, excuse me, when two um, tectonic plates are moving away from each other in a divergent plate boundary. This can also cause normal faulting. Um, which is when you get a fault where pieces of plate are moving away from each other, right? Um, there's a whole region of the US called the Basin and Range Province, which is a whole bunch of normal faults stacked next to each other, where a large section of the interior United States has been stretched thin by various tectonic forces, causing that whole range. And it is a mountain range because you have mountain valley, mountain valley, mountain valley, but it's actually been formed by the result of stretching rather than compression. It's a very interesting place. Then we have shear stress. Now, shear stress is the tricky one to visualize. This is where we get shear stress is responsible for the formation of a lot of faults. Now, shear stress can occur in compressional zones, transform plate boundaries. Shear stress is when you have forces applied to a body of rock or to a region at various depths. So here in this bottom image, you can see there's force being applied to the right in the top layer, but to the left in the bottom layer. And this is going to create an unequal distribution of stresses on my body of rock, which is going to cause them to deform in pretty weird ways. We can get some very interesting faults as a result of this. Um, as a matter of fact, these are responsible for making entire fault zones that are just highly faulted areas as a result of the application of shear stress. All right, so deformation. There are several different ways that rocks will deform in response to these various different types of stresses. The first one is elastic. Remember our good friend, the rubber band here. So this rubber band is getting stretched, it's getting stretched, and what's happening? We're building up that elastic energy. Well, eventually you reach a point where that energy has to be released. Either the rubber band snaps, aka your material cannot take that kind of stress anymore, or it slips out of your hand and returns to its original position, right? Its original shape. But as it does so, it releases all that energy that it built up into the air around it. Yeah. That's called the elastic limit. Um, Either the release of that energy through the breaking of material or the release of that material because the friction holding it in its new position is no longer strong enough to overcome the elastic energy that is built up. Okay, so that is an elastic deformation type. Then we have brittle deformation. We're all familiar with this. We've picked things up, we've dropped things, they break. Your phone screen will break. Your delicious chocolate treat, when you drop it on the ground, it breaks. Any number of things break when enough stress is applied to them, and they break into pieces. This is called brittle deformation, like the brittle tenacity in minerals. Just like this unfortunate fellow who's just had it with his day at the office, throwing his computer at the window. I've had days like this, never actually thrown my computer, but there are days that I definitely wish I could. I'm sure we can all relate at one point or another. But that window shattered, it deformed brittly. Okay, the ability, the strength inherent within that material was passed, and the material shattered as a consequence of the energy he applied to it with his thrown computer. Looks like he threw a Mac, so I can completely understand his frustration and why he threw it. Sorry, I'm a Windows PC guy. All right, and then there is ductile deformation. In ductile deformation, your material will deform according to the pressure applied to it, and it will retain that shape. There is no breaking here. It simply reforms itself according to the pressure applied. I hope that sounds familiar to a lot of you. How is what form is this? Or excuse me, what does this sound like? It should sound very similar to the glaciers lecture that we had, where we learned about plastic deformation. Plastic deformation and ductile deformation are very similar to each other. Okay, think of them as about the same within these contexts. Okay. So, what controls how my materials deform and what type of deformation? Well, obviously, of course, there is the material involved, the rock type. Okay, that's the first starting characteristic. Is it gneiss or is it granite? Is it basalt? Okay, all of those are they have high temperature ranges or high temperature constraints. They generally, in normal conditions, will deform brittlely. They will shatter. They will break. Okay. Then you've got things like limestones and marbles and salts that are actually pretty soft, pretty pliable, ductile. They're naturally more ductile than the other materials, but under certain conditions, they become even more ductile. We'll talk about that here in a second. Um, Temperature is the next factor that controls this. Remember that example I've used before of your Hershey's chocolate bar. You buy a Hershey's chocolate bar, you throw it on the dashboard of your car, you get to work, you leave, you go inside. 30 seconds later, oh no, I left my chocolate bar on the dashboard of my car. You run outside, you grab it. It's no longer nice and hard. It didn't take long for that chocolate bar to become kind of soft and it's not melted, but it's a little mushier, a little softer. It's ductile, right? It's flexible. It's still a solid, but it's still flexible, right? Temperature plays a role in this with pretty much all materials, okay? Higher temperatures generally mean more ductile behavior in a material. Then you've got your pressure. As you increase your pressure, you're going to increase your ductile materials ability to flow in a certain direction. Okay. So if I were to ask you, do materials tend to flow towards zones of lower pressure or higher pressure? What would you say? I hope your answer is lower pressure. Everything flows from a high pressure zone to a low pressure zone. That's why we have wind. That's why we have ocean currents. That's why we have a lot of these things, high pressure to low pressure. So when I have an increased zone of pressure, it's going to push ductile materials out of, excuse me, out of that zone and into a zone of lower pressure. Okay, so remember all that. Now, these three factors add up to some very interesting phenomena that we see in the world. The first one being a salt dome. You've probably heard the term salt dome before if you're at all familiar with the oil industry, and if you have not, then let me give you a quick rundown on what a salt dome is. A salt dome is essentially a plume of salt from underground that has risen upward near the surface, but has been capped by some other form of rock and has kind of ballooned into this big bubble shape under that layer of rock. All right, so how does this happen? We have layers of salt deep underground that are hundreds of feet thick. Okay, I know this sounds really hard to comprehend, but we actually have a lot very close to here in Odessa. Okay, so the Gulf of Mexico, the bottom of the Gulf of Mexico, and the coastlines around it are covered, or I shouldn't say covered. There are lots and lots of salt domes underneath the layers of rock out there. Okay, lots and lots and lots of salt domes, and you can see them when you look at a gravity map. If I were in my classroom and I had access to show you this, I would show you a gravity map of the um, Gulf of Mexico. You can actually Google this yourself if you want. I give you permission to do that. You can Google gravity map of salt domes in Gulf of Mexico, and you will see all of these sort of bubbly, blistery shapes at the bottom of the Gulf of Mexico. And those are all salt domes that are near the surface. So we get these layers of salt from deep underground, which in our area in the Gulf of Mexico, they formed millions of years ago, 100 million years ago, about when the Gulf of Mexico, when the water that was where the Gulf of Mexico is now, evaporated away, leaving behind thick layers of salt. And this happened over and over and over and over. And so you get salt gypsum, all these evaporate deposits that eventually got covered in other layers of sediment. Well, as the pressure increases and the temperature increases down there, it makes my salt more ductile, and that pressure is going to force my salt somewhere to a zone of lower pressure. If there is a crack, like a fault, for example, in the layers of rock above my salt, then that salt under that pressure is going to ductily flow up through that crack, through that zone of weakness. It's going to push its way up there, widening that crack out until it goes up high enough that it reaches a layer of rock it cannot pass through, usually some other ductile layer. Something like shale or a limestone is pretty common to act as a cap here. So it reaches that area and it kind of pushes that top cap rock upward a little bit. But what that does is it makes a zone of low pressure around the sides of the salt dome. Now, that concept of materials flowing to zones of lower pressure is true for liquids as well. Let's say we have some oil in the vicinity. Maybe it's trapped in a layer of sandstone that you see this particular example has cut through. The salt dome has cut through a layer of sandstone, that yellow layer. Well, the oil is going to flow through that porous, impermeable layer of sandstone until it comes to a zone of lower pressure. In this case, the area around the top of my salt dome, because it has pushed a bubble of rock up above it, making a zone of lower pressure nearer the surface. So the oil is going to pool around my salt dome here. Now, this is actually why we have so much oil production in the Gulf of Mexico, because there are all these salt domes, and all these salt domes have massive pools of oil built up around the perimeter. Whenever we find a new salt dome, it's pretty common companies invest a lot of money into determining whether or not there is enough oil there to exploit, and there usually is, which is why we have so many oil, um, um, so much oil being generated in the Gulf of Mexico. All right. Now, we actually have salt domes on land as well. If you ever drive down Farm to Market Road, 1053, um, uh, going generally towards Big Bend, um, you're going to notice that there is a giant pit off to the side of your road at some point. I forget which mile marker it's at, but there's going to be a giant pit out there off to the right. And that giant pit is where a salt dome used to be. But some oil company tried drilling down to access the oil next to it, and they accidentally introduced the local groundwater to the salt dome, which is a big no-no. What happens when water and salt meet? You dissolve the salt, right? Well, as the salt started to dissolve away and get carried away in the groundwater system, what does that do? It leaves a big open gap underground. A big open gap eventually is going to collapse down into itself. And that's why there's a giant pit off to the side of the road on Farm to Market 1053. Okay. And it's actually still growing as that salt dome continues to dissolve underground. Occasionally, every now and then, they do have to move that road a little further away. All right. Now, the other concept here is time. As time goes on, these deformation factors only get more and more exaggerated and larger as time goes on. All right, so some other examples of deformation structures. We talked about salt domes. Folds. We've talked about folds in the terms of metamorphic rocks. Now let's talk about them um, for themselves. Okay, so there are two types of folds. Excuse me. You have your anticlines, which are convex, so an arching shape. So this bottom picture on the left there, that's like that arching shape is an anticline. Then we have a syncline, and those are your troughs. Okay, so the ones that dip down, like you see in that middle picture there. Okay, anticlines and synclines, and you'll often find them in pairs because the same forces that make one typically will form another as well. So what goes up must go down, right? So physically speaking, they will often form pairs. And so you'll see anticline, syncline. And then depending on how intense the forces were that caused this, you could see anticline, syncline, anticline, syncline, anticline, syncline. Kind of like a sound wave almost going through the layers of rock for however long a distance, however far that force, that compressional force in this case, um, uh, affected the layers of rock. Now, this picture on the right is demonstrating something called plunge. Um, Layers of rock are deposited horizontally. We talked about this early on in the class, the principle of original horizontality. All layers of sedimentary rock are deposited horizontally to begin with. Why? Because if the sediment was at a steep angle, it wouldn't have deposited, right? It would have kept on flowing right down that slope. So for that sediment to have deposited in the first place, it has to have deposited horizontally and then turned into rock. And then later on, those layers of rock got tilted by tectonic forces. What happens when I take some layers of rock that have gotten tilted and then fold them? Okay, I'm going to get a fold where one side of it is plunging into the ground. And so what that's going to look like is kind of a spear point on the end of your layers of rock. So you can see, maybe, I hope you all can see my mouse here. Um, let's see. I don't think I can change my mouse into something. Pointer options. Here we go. Nice. Laser pointer. Hey, yo, look at that. Okay, so hopefully you can see this. See this layer of rock right here curves around this end and is the same layer of rock right there. Okay, this is the same layer of rock. It's just that this particular fold is plunging into the ground, going towards the bottom right of my screen, which means that on the surface view, if I were to slice that fold in half, which is what happened because of weathering and erosion here, I'm seeing that same layer of rock curve around this way. And this is how I know what direction it's plunging. It's plunging down that way because this is where I'm seeing that layer of rock curve around. Okay. Same with this red layer of rock. Okay. And this yellow one around that white one we were just looking at. So how do I know if this is an anticline or a syncline though? That's the trick. It's not easy to tell. That's when we actually need to go and collect some samples and look at it. Why? Well, we've learned about the principle of original horizontality, but also there's a law of superposition. Can you remember what the law of superposition is? The law of superposition states that whatever's on the bottom is oldest and whatever's on the top is youngest, right? So if I have originally horizontal layers of rock and then they get folded into an anticline, my oldest layers are going to be the bottom part of the fold, right? The youngest layers are going to be the top part of my fold. Now, what would happen if I were to slice this anticline down the middle? Weathering and erosion has taken its toll, and at the surface view, it's been sliced, and everything above this line I'm drawing is gone. What do I see in the middle of my sliced anticline? In the middle is going to be my oldest layer peeking up through. And on the outside, my youngest layers peeking up through. Okay? What about in a syncline? In a syncline, oldest is this bottom fold, youngest is this top fold. If I were to slice right here at a top view, my youngest rock would be in the middle, my oldest rock would be peeking up at the sides. This is how we tell. Is this an anticline or a syncline? Well, what are the relative ages of the rock? If the youngest is in the middle and the oldest is on the outside, this is a syncline. If my oldest is in the middle and my youngest is on the outside, it's an anticline. Okay? Come on now. Oh, is it not gonna? I don't think it'll let me progress if I have a laser pointer on. Nope. Okay, interesting. Okay, so that same concept is true with less linear formations as well. In a fold, you see it stretch for miles and miles and miles and miles, however long that fold is above the ground. But what happens when the same sort of tectonic force occurs in a more local or regional setting? Um, let's talk about that. A dome is when some tectonic force or magnetic force, this can happen when a magma chamber is rising up through the ground, pushes the rock above it upward. Okay, it pushes the rock above it upward, makes sort of a dome shape. Okay, and then other layers of rock get deposited on top of that dome. So what do we have here? If that gets sliced because of weathering and erosion, okay, so materials removed until we're looking at it in a kind of a 2D viewpoint, the oldest rock, which is my granite, is going to be here in the middle. And the younger rock that was deposited on top of it in that dome shape is outside. So you get this sort of bullseye shape where the oldest rock is in the middle. All right. So now let's talk about the other way, the opposite. A basin. A basin is a low-lying area. We live in a basin. Why do we call it a basin? Not because this is currently a region with a lot of deposition, but because in the past was a low-lying area that got filled with sediment. Okay, the Permian Basin is a basin that is already filled with sediment. So in this bottom picture here, this kind of A to B cross section, you're seeing this low-lying area that layer upon layer of sediment have been deposited in. Okay? Law of superposition, whatever was deposited on top is the youngest, right? So just like with that syncline, the youngest is in the middle and the oldest is on the outside of our bullseye shape. Okay, the entire state of Michigan is essentially a big basin bullseye. Okay, with the youngest in the middle, and then each bullseye layer getting older and older as you move outward from that middle area. Okay, you're looking at a larger view of something like this. Okay. All right, a little bit more about faults. Most faults occur in the top 15 kilometers of crust. I want you to think about why that is for a moment. Leave a comment if you like, talk out loud, converse, however, just work it out in your head for a minute. Okay, let's talk about this. Most earthquakes occur in the top 15 kilometers of crust. Why is that? Because most faults are in the top 15 kilometers of crust. Why is that? Remember what we talked about how temperature affects the behavior of materials. The harder your material gets, the less brittle it is, the more ductile it is. If a fault is a crack in the earth along which stress builds, then why would the earth crack when it's behaving more ductily? So the deeper you go underground, the higher that geothermal gradient gets, the more ductile our material behaves, the less likely it is to crack into a fault, and the less likely you are to have earthquakes that deep. All right, so most of them occur fairly shallowly. Okay. Um, Faults have some kind of offset, and depending on the type of fault it is, it'll either be vertical or horizontal. In the case of a normal fault and a reverse fault, there is a vertical offset. Why? Because in a normal fault, the hanging wall is moving down relative to the footwall, and in a reverse fault, the hanging wall is moving up relative to the footwall. In either case, you're going to get one side that's at a higher elevation above the other, and that's going to make some mountainous area on the side that is above the other side. So this is where that um, kind of that mountain valley pairing that I talked about before comes from. Now, with your strike slip faults, you're going to get horizontal offset. So this is pretty easy to see if a fault occurs wherever there's some linear feature like a river. Okay, so wherever a river occurs, um, and you see it kind of jukes one way and then the other, you might be looking at a strike slip fault that goes through the river system. Okay. Same thing is true for valleys. Same thing is true for mountains or foothill areas. Roads sometimes will move and be deviated with the movement of strike slip faults. Just any linear feature that crosses that boundary, you'll see that horizontal offset. Now I'm going to introduce a different type of fault to you called a thrust fault. A thrust fault, which you can see in the bottom left here, is the type of fault you get when compressional force, that compressional stress, causes one side to move above the other side, just like with a reverse fault, with the difference being it's a much shallower, lower angle fault system. Why? Because the stress did not cause a fault to break through the layers of pre-existing rock like it does in a reverse fault or a normal fault. Instead, the stress caused a fault boundary to occur between two layers of rock, okay? Which means that we get a much shallower angle fault system here. Now, thrust faults tend to move a lot further than reverse faults do. Why is that? If you said it's because the lower angle means you have to fight gravity less, you're absolutely correct. There is less gravity to fight at this low angle fault. And so thrust faults tend to go very far. As a matter of fact, up to a substantial amount of the Rocky Mountain and associated geography in the middle of our country are the result of multiple sequences of thrust faulting from the west coast moving east. We'll talk about that in 1404 when you take that class. Any mountain building event is called orogenesis. Okay, orogenesis is the process. The event is called or an orogeny. Okay, so we'll learn about different orogenies in 1404, but the process itself is called orogenesis. Let me talk about the different types of mountains that we see as a result of orogenic processes. Volcanic island arcs, which you see in the bottom left here. This is what happens when two ocean plates converge with each other and one subducts underneath the other. But wait, Professor Hart, you told us that when two plates interact with each other, the denser one is the one that subducts under the less dense one, which is why ocean plates subduct under continental plates. So why would one ocean plate subduct under the other? That's very true. Can you think of any reason why one ocean plate would subduct under another ocean plate? Under what circumstances would one ocean plate be denser than another, in other words? When one ocean plate is older and colder and a little thicker as because of its age, then it is denser than the newer plate. And so the older plate will subduct under the newer plate. Now, this is going to cause a volcanic island arc to occur on the boundary of the newer plate, the overriding plate, as that ocean plate dives into the mantle, taking water with it, lowering the melting point, creating the magma that rises to the surface and makes volcanoes. We get our volcanic island arcs. This is where we get places like Japan. It's a volcanic island arc. Okay. Then you got your Andean type mountain ranges. These are the ones that form through the same process, but an ocean plate subducts underneath a continental plate. Same process occurs, water is introduced to the mantle, you get the same magma bodies rising, the exception being they become intermediate and felsic by the time they reach the surface, meaning that we get a large, tall, Andean type coastal mountain range built up on our continental side. An accretionary belt is what happens when that volcanic island arc runs into that Andean type convergence zone. And the volcanic island arc gets scraped up onto the side of our continent. Now, this can happen over and over and over and over again, and that's how you get places like California. California, pretty much the entire state, is a conglomeration of volcanic island arcs that have gotten scraped up onto the side of North America. Trying to untangle that mishmash web of islands and original North American rock is something that takes entire careers to figure out. Then we have collision belts, which is a straight up collision between two continental tectonic plates. And that's where you get your Himalayan style mountain ranges. As they collide with each other, neither one is more dense than the other. And so the colliding energy causes material to get pushed high up into the ground, into the atmosphere and deep underground, making a thick mountain range. And then the other way that we can get mountains, not built so much as continued, is through isostatic adjustment. If I were to put blocks of wood in water, they would float. But if I were to cut some wood off of those blocks, the same proportion of wood would be floating above the water as there was previously. No matter how much wood I cut off, some amount of it is always going to be floating above the water. Why is that? This is called isostasy. It has to do with buoyancy of one material over another. As I weather and erode the material off of a tall mountain range, it is going to be losing mass on the top of that mountain range, which one would think causes the mountain to lose altitude, to drop in elevation. And it does to a point, because as it is losing mass on the top and that mass is being carried away, the mantle underneath of that mountain range is pushing upwards on it because it is becoming less buoyant by losing that mass. Or it's not because of it becoming less buoyant, I should say, it's keeping that same ratio of buoyancy. So just like with that wood, no matter how much I cut off the top, it's still going to float some amount above the water. The same thing is true for mountains. And so the bottom of my mountain range is going to push upward out of the mantle as I'm removing mass through weathering and erosion on the top. Eventually, when you have really, really old mountain ranges, you end up with very low, very uh, short mountain range that is made almost entirely out of the deep, deep underground crystalline metamorphosed rock that formed way underground when that mountain range was brand new. It's called isostatic adjustment. All right, my friends, that's the last of the material I have for you in the class. So we're going to move into the final exam review now. I'm going to go ahead and pull up my email. I actually haven't had an opportunity to check it yet today. So I'm going to leave the screen blank. I'm going to leave it black so you don't see everyone's emails that have been sent to me. That would be unfortunate. And I'm going to jump over here to my messages and see if anyone has sent me questions for the lab or for the exam review. Okay. None in that class. Or in that class. Boy, this could be a very short exam review if no one sent me questions. I know every now and then I'll get students that complain, well, how come you have us ask questions for the exam review? How come you don't just have like a piece of paper or something that to guide us? And I'm like, well, because all the information that you need is in the lectures I've given. What possible better review could there be than for you to tell me where you're lost, what you don't know? That's honestly the best case scenario for an exam review. It's just a matter of people sending me questions because they know where they're lost, whereas I don't. Okay, so no one has sent me any messages over Blackboard. Let me go ahead and jump into my email here and see if anyone asked me any questions there. Okay. No. No. All right. That's pretty straightforward. No one sent me any questions. So let me just do this, okay? I don't want this to be a completely useless exam review. So let me just give you some information and hit on a few highlights for you, okay? Again, I'm going to leave the screen blank here. I'm sitting in a dark room, and frankly, I am not dressed or put together in a place where I want to have the camera on. So we're just going to do it like this. All right, so your final exam is going to have 45 questions. Why so many? Well, because it's cumulative, okay, friends? It covers everything from lecture 1 to lecture 13 that we just had. Um, um, excuse me. Finals week, not a good time to get sick as a student or a professor. Where was I? Oh, 45 questions. Yes. Okay. So they cover all of all the material from lectures 1 through 13 is fair game. Okay. So there isn't any one thing I could tell you to study more. If I talked about it in the class, it has the potential to be on the exam. Okay. I wouldn't have covered it in the class if it wasn't important enough for you to know. That being said, you do have the normal 500-minute time limit to take all of these questions. That's more than 10 minutes per question, my friends. And there are going to be true false questions, matching questions, whatever that you're just like, you breeze through it in 10 seconds. Put some thought into it, obviously, but some of these are going to be easier than others, which is going to leave you lots of extra time to do the things like the short answer questions. My recommendation to you would be, and I've said this before, go through the whole exam, just like take a look through it, see where the short answer questions are, maybe prioritize giving time to those because they tend to be worth the most points. Answer all of those, and then go through and do the shorter format questions. And if you answer a shorter format question that jogs your memory and you're like, oh, I can I can be more specific on that one short answer question because of what I remembered by answering this question. Go back and redo your short answer question. It's not submit one question at a time. It's all in one page. So you can go back and edit something before you submit the whole exam. Do not start the exam and then leave and come back. I've had more than the average, more than the normal amount of students who said, "Hey, I started the exam and then I had to go to work and I came back and auto submitted." I had way more of that this semester than I ever had before. I have not changed the format of this exam, and frankly, I'm not going to. This is the best way that I have determined after 5 years of teaching these classes. This is the best way that I have determined to evaluate student performance. And I have made a few changes over the years, but I have not yet found a better system than this. Um, do not ignore my advice and start the exam and then leave and come back to it. Don't go take a nap. I mean, maybe you can stand up and stretch, maybe grab a snack or a drink for a few minutes, but don't like leave wherever you are. Come back and finish the exam, my friends. I will not reopen it for you. Some of you have asked me to for former exams, and I have when the circumstances seem appropriate, but for the vast majority, I have not. I can go and see every single thing you do in the Blackboard. Every time you log in, everything you click on, every assignment you click on. Which means, yes, for those, I'm kind of calling people out here, but I think it's justified because of actions that you have taken. For those of you that complain to me that my class is not an adequate way of teaching an online class, but you didn't even log in until the last week of the semester, I know. So your argument is invalid because you chose actions, and I can see whether your stories add up or not. I know I'm coming off kind of harsh here, but to be frank, I've put more thought into this class than you have. So I think it's fair. Um, do not shoot yourself in the foot. Okay, my friends? Give yourself the best possible advantage. I know a lot of you are overworked. I know a lot of you are overstressed. I completely get it. I am too. If you only knew how many days of the week that I stay at the college grading things until midnight to try and get them to you in good time or to get them in before due dates or anything like that. Um, because of all the other things I'm balancing my life just like you are. I get it. But you have to prioritize this. It's finals week. Push through, stay strong. Okay, you can do this. All right. Monologue over. Now time to move on to another monologue. Okay, so you can use your notes. Do not use AI. Do not use Google. Several people this semester have already been warned about using AI, and I have given them the punishments that I said would come associated with that. Those that have used AI on an exam have failed that exam. Any second-time offenders, I fail in my class. Don't let that be you. Like I mentioned at the beginning of the course, there's usually one or two that try it for a first time. There's only ever been one student that tried doing it a second time, and I did fail her in my class. Um, don't let that be you, please. Please. I really don't want that. Your priority is to get a good grade. I get that. My priority is for you to learn. And so if the struggle is between me deciding, okay, they used AI and they got a good grade, or they used AI and therefore they didn't understand, I am always 100% of the time going to err on the side of I value you understanding more than your grade. And so your grade will suffer if I don't think you got the understanding. That's my job as an educator. And frankly, it doesn't matter to me if you agree with it. That's how I view it as an educator. So don't let that be you. Um, what else? What else can I give you about this? I would say that it is going to be more beneficial to you to review the first module of your notes. Okay. Put extra love on those, put extra attention on those as you are preparing for this exam and as you are taking it, because that's the content we covered the furthest amount of time back. Okay. Module two, you got a few weeks ago. Module three, you got this week. Okay. So module one, it's a little more rusty in your head, maybe. So put a little more love into reviewing your notes for that. Um, and what else? Oh, speaking of notes, please don't forget to submit those. You should, all of you, have taken notes during this class, and you all deserve the extra credit as a consequence of taking those notes. Please submit those notes, and I will give you the extra credit that you deserve for doing so. Okay? Again, that extra credit, all extra credit for my class, gets put on the lowest exam score. So it can save you. It's a one-off save. It won't save you from two bad exams, but it will save you from one bad exam. Okay. um, the only other thing I can think of to say is um, thank you for taking my class. I really appreciate it. I appreciate the dedication. I appreciate the time you've put into it. I appreciate the interest you have shown. My in person students, we had some fantastic conversations. My online students, I got emails from you asking questions and asking for clarifications. I value all of that. My only regret is that I can't have the same level of interaction with my online students that I do with my in person students. I really wish I could, but we're not there technologically yet. We're getting closer. There are a few tools that I've used in the past that almost got there, but came at a cost to the students. And so I removed those from the course because my students would have to pay $30 for those services. And I had more students complaining about the cost than who gave me positive feedback for the service. So hopefully one day we get something similar that doesn't come at a cost to students, so that we can all have that level of interaction that we crave so much in these courses, especially in science courses. But I really, really, really appreciate all of you for taking my class. I hope that some of my enthusiasm for the sciences has rubbed off on you, not to the point where you might, want to uh, become a geologist, although that would be cool. Um, but at least to the point where you are more informed, more interested, and a little more enthusiastic about an amazing world that we live on and a universe that we live in. And yeah, thank you so much for taking my class. If any of you online or in person are ever in the Wood Building, feel free to stop on by my office. Come say hi to the animals, stop and chat. I'd love to talk to you. But good luck on the final. Y'all have got this. Give it the time and attention it needs. Finish strong. And I'll see y'all later. Thank you very much, everyone.